Okay, resonance structures. Today we're going to look at resonance structures, kind of what they are, as well as going ahead and drawing a few, and then being able to determine using formal charge what resonance structures are best. You guys feel really close to me today, like really close. I'm usually not this close. Anyway, so looking at these three resonance structures, these were actually some that we drew yesterday. These are the three resonance structures for nitrate. It's important for you to realize that the actual structure that we can visually, if we take some sort of electron picture per se of our hybrid of resonance structures, we would actually see something we wouldn't see something with two single bonds and a double bond. We'd kind of see something that's an average of that, where every bond is about 1.3 in length. Does that make sense? So basically, your resonance is an average of those structures. And it's not that these are necessarily three different structures. We actually have electrons that can resonate. So I'm going to do some drawing on here just to show you where the electrons go to make one thing and the other. So for instance, if this first one was going to become the next one, we would move a lone pair from here up to that, and that would make nitrogen positive because it just lost some electrons. So these would then go down to make nitrogen happy again and bring us back to neutral. So we'd have that shift. And if this one were to become this one, these would go up to here, and then these would come down. So that's the kind of resonation that's happening with all of these electrons. All right? So this is continually going on. Right here it says electrons are really delocalized. They can move around the entire molecule, and that's what's happening with those arrows. And part of what you learn in organic chemistry is how to do resonance structures moving these things. Go ask any organic. So tell me about drawing resonance structures and see the look they give you. It probably won't be a very nice look. But all right. So we already did CO2 yesterday, so I'm not going to draw those, but I'm going to now introduce the concept of formal charge, and then we'll tie it all together. Formal charge is basically finding a value for every single atom in a substance, a charge value. And the sum of those charges of every single atom will be equal to the overall charge of the substance. So this POCl3 is neutral. It's not an ion. So the sum of all the formal charges should be 0. So how do I calculate formal charge? This looks like a really scary equation. It's not. I'm just going to show you what to do. I'm going to start with this chlorine right here. First thing you do is you take the number of valence electrons that chlorine has. How many valence electrons on the periodic table does chlorine have? 7. Minus, now you got to watch me. You subtract 1 for each lone electron and then 1 for every bond. So 7 minus 1, 2, 3, 4, 5, 6, 7. 7 minus 7 is 0. So the formal charge on this chlorine is 0. Let's do oxygen. Oxygen has how many valence? 6. 6 minus 1, 2, 3, 4, 5, 6, 7 is -1. So we're going to do a little negative here. And you're going to write them close to the elements. We need to have a formal charge for every element. Chlorines, if you look, they're the same. They're going to be 7 minus 7. So this is 0 and this is 0. Now we need to do a formal charge for the phosphorus. How many valence electrons in phosphorus? 5 minus 1, 2, 3, 4. So what is that? Plus 1. So do you see how a +1 and a -1 cancel out? Make 0. That's why the overall charge is 0. So once you start assigning formal charges to things, I'm not going to require that you use the big brackets on the ions with the charge on the outside. It would be redundant if you did both. So you're allowed to figure out, okay, if the nitrate is, well, let's go back. If nitrate were -1, which it is, where is that -1 coming from? So in lieu of these, you could actually just find the element that has, or find what elements are charged, what's making it have an overall -1. So let's start with this oxygen up here. 6 valence minus 1, 2, 3, 4, 5, 6, 7. I'm right there. 6 minus 7 is -1. Okay? Let's go to the next to the right oxygen. 6 minus 6 is 0. We good? Nitrogen has 5. 5 minus 1, 2, 3, 4, 1, 2, 3, 4 is +1. And then this oxygen is 6 minus 1, 2, 3, 4, 5, 6, 7, and that is negative. So that has a negative, this has a positive, and that has a negative. Do you see how it's overall a negative? Okay? So again, if you do formal charges, you don't need brackets, because that's being really specific. So what is formal charge really saying? If you have a formal charge of 0, what you're saying is you have, or whatever atom has as many electrons in the structure as it normally does in valence, right? So that's really stable. That's a really, really happy, stable atom. What if you have a negative formal charge? What does that mean? You have more electrons than you normally have in valence, right? So tell me about what kinds of atoms, what would be the atom that would most love to have more electrons than it should? Fluorine, right? So the more electronegative your atom is, the more accepting or more stable it is to have a negative formal charge. So that's kind of going to lead to how we decide what structures, resonance structures, are best. So let's go ahead and look at these rules. Rules governing formal charge, and then we're going to talk about the whole why CO2 double bond is better. The sum of the formal charges of all atoms in a given molecule or ion must be equal to the overall charge. And I showed you that in 2 instances today. If non-equivalent Lewis structures exist for species, those with a formal charge closest to 0, and with any negative formal charges on the most electronegative atoms, those are the most stable. Those are the best. So that's how we choose. So let's look at our Lewis structures of CO2. We really have an additional one here. What's the extra one? What's my extra resonance structure for carbon dioxide? Single, then triple. And this is why it is crucial that you have those lone pairs of electrons, because you can't calculate formal charge without them on any atom. All right? So let's start here with this first oxygen. What's oxygen's valence? 6 minus 1, 2, 3, 4, 5 is +1. Carbon, 4 minus 1, 2, 3, 4 is 0. 6 minus 1, 2, 3, 4, 5, 6, 7, that is -1. All right, and this will be the reverse. This will be -1, 4, and +1. 1, 2, 3, 4, 5, 6, 7. Oh, the carbon 0. You know why I wrote 4. I was thinking 4 valence. Okay, yeah, 0. Okay, so now we've got those. Let's do CO2 over here. Oxygen is 6 minus 1, 2, 3, 4, 5, 6. What is it? 0. 4 minus 4. 6 minus 6. 0. Do we see why this CO2 is now the correct, well, not the correct, the most common resonance? It's the one that's going to be the largest percentage existing in the largest percentage. Why? All our formal charges are 0. So when you're asked, to draw a Lewis dot, and you have a bunch of resonance structures, and I don't say draw all resonance, you need to draw the one that's best. So if I ask for CO2, I expect to see this one. Unless I say draw all resonance structures. Okay? So let's practice another one where we actually draw now. This will help review us for our quiz. Write 3 different molecular arrangements for CNO using formal charges. Determine the most stable. All right, needed, available, shared. We got to draw these. How many do I need? 8 times 3 is 24. How many do I actually have? 4 plus 5 plus 6 plus 1. Okay. Why did I do plus 1? We have that negative extra electron, right? So 24 minus 16 is 8. So we have 4 bonds in our picture. So what element are we going to put in the middle? Carbon. So we're going to put carbon in the middle. I'm just going to get my, I know there's going to be 3 resonance structures here. So I have 4 bonds, so I can do 3 and 1, and I can do 2 and 2, and then I can do 1 and 3. And so on this side I have, it doesn't really matter, I'll put N here and O here, and I'll leave it N and O on both sides, on all of them. Of the 16 electrons, I've used up 8 in bonds, so that means I have 8 to pass around, so 4 pair. So here's 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. You can't skip adding those valence electrons in there. You have to, so we can calculate formal charge. So now we're going to go through and to all 9 atoms on this paper, we're going to assign formal charge. Here we go. Nitrogen is 5 minus 5 is 0. Carbon 4 minus 4, 0. Oxygen 6 minus 1, 2, 3, 4, 5, 6, 7, negative 1. All right, middle. Nitrogen 5 minus 1, 2, 3, 4, 5, 6. Carbon 4 minus 4. Oxygen 6 minus 6, 0. All right, and then last one, nitrogen 5 minus 1, 2, 3, 4, 5, 6, 7. Minus 2. Do you think that's a better or worse situation to be in? Worse. The further away from 0 you get, the worse off you are. 4 minus 4 is 0, and oxygen is 6 minus 1, 2, 3, 4, 5, plus 1. So which one do you think you can immediately throw out? The last one, yeah. Oxygen at a plus 1, not good. What is that saying? That's saying oxygen has one less electron than it normally does, and oxygen's pretty gosh darn electronegative. So that's not a happy state for oxygen. So this one we could totally get rid of as not being the most stable. So of the remaining 2, which one and why? Matthew? Exactly. This is the better choice because this oxygen is more electronegative than that nitrogen. So that's where that negative 1 wants to be. That's where that extra electron is most stable. So if I asked you to only draw one structure, you would have to draw this one. So might that need you pulling out a piece of scratch paper, drawing all 3 and figuring it out? And then, yeah, it could mean that. All right? How do y'all feel about this? Do I need to do the other one? Because if you look, it's literally all the same, except instead of oxygen, we use sulfur. And sulfur has the same number of valence electrons as oxygen, so like all 3 pictures are literally the same except for sulfur being replaced. Let's at least, let's do it because some of you will struggle with the what's more electronegative part, sulfur or nitrogen, so let's go ahead and do it real quick. Here we go. So you can basically draw these identical, except replace your sulfurs, oxygens with, your oxygens with the sulfur. Same number of electrons. So that's what I'm doing. I'm literally copying what I had done here. Oops. Sulfur. And then okay, so just practicing formal charge. 5 minus 1, 2, 3, 4, 5 is 0. 4 minus 4 is 0. 6 minus 2, 4, 6, 7 is negative 1. 5 minus 6 is negative 1, 0, 0. And this one, 5 minus 2, 4, 6, 7. 2, 4, 6, 7 is negative 2. 0, and 6 minus 1, 2, 3, 4, 5, plus 1. So everything's the same. What do you think this time? Level takes precedence. Nitrogen's what? So the one correct. This is our better option because nitrogen is more electronegative. Now, I think there's going to be some people out there in chemistry land across the ocean, who knows where, that are watching this and are going to be, nitrogen always triple bonds, so that can't be the answer. based on electronegativity values, this is more stable based on normal formal charge rules. So that's where we're going to leave that. Okay, any questions on this? No? It's pretty easy, and it's going to become something like in organic, they can like do formal charge almost without even looking at it. Like it's innate. It's as simple to organic now as it is to y'all naming a compound. I mean, it's that common and that important. So hopefully you'll get used to it. All right, I'm going to give you a few minutes to study for your quiz, probably like about 5. So go ahead and do that.